Okay, so let us continue. So last time, right, we transitioned, right, to so-called review, right, of random variables. And the emphasis, right, is that random variables, uh, just like any other probability concept, right, is crucial for, being able to work with stochastic processes. Now, so two things that basically we want to know about not want to know, but like like sort of like the theme, right, that we want to know about the random variables are as followed. So you need to know the common random variables, right? Like the Poisson, the normal, the binomial, the Bernoulli, the exponential, right? And the geometric, the negative binomial, right? Basically the common ones, the uniform. So you need to know what? You need to know their distribution, meaning either their density function or their mass function, their expectation and their variance and their connections, and possibly, right, the conditional distribution of, some of them. We'll look at that. But so basically, right, by knowing, we don't mean just, being aware of, but you need to be very familiar with these knowledge or like memorize them, okay? Because if you don't memorize these, then when you have to deal with like more complex problems, right, involving these random variables, then you won't have an idea of, right, how they behave, what they look like, and your intuition cannot go further. But that's so basically all this stuff should have been covered in a probability theory, right, course. But I guess a more, let's say, advanced one still should be covered, right, under the theme of a probability course, is the idea of sum, right, of ID random variables. Okay, so pay attention to this theme when we go along this lecture. It shows up here and there, and it'll show up more, okay, in the next lecture. But so first of all, right, why is sum of random variables important? So the idea, right, is if you have a random variable x, and you can write as a sum of xi, okay? Now, so it depends on the assumption here, but let's say we assume that these are IID. And then, and of course, right, the whole point is that compared to x, the xi are simpler, meaning it's easier to work with, right? You can work with, the expectation, their variance, that kind of thing. So can easily be found, right? Then the first thing is that expectation of x in this case, right, by linearity of expectation, will be just the sum expectation of xi, right? This is always true. So, right, if you know this, then you can just sum the expectation of xi and get expectation of x. Always true. So, right, that's one benefit of paying attention to the sum. The variance is more complex, right? The variance will be the sum, right, of the individual terms only if xi are independent. So here, right, if we say IID, then yes, right, one of those I indicates independent. So, right, that works. And so, right, again, you can just plug in and find the variance of x, right, via the variance of xi. But a more general formula, right, will be variance of x, right, will be the sum of the variance of xi plus, right, twice the covariance. Sorry, well, here you want the sum, right? I less than j covariance, right? So this is the general formula. This is always true again. And so this, of course, right, is more complex in the sense that it involves covariance term, right? But once again, if the xi's are simple or simpler or simple in structure, then, right, working with this sum is still much easier than working with the x directly. And so, right, the structure of representing a random variable as a sum of other simpler random variables, okay, will be a crucial technique or an important structure that you see basically, right, in a lot of places in stochastic processes. Now, so as a demonstration, right, for example, we looked at, right, the binomial, for example. Now, if you want to find, let's say, expectation of x, all right, and if you want to, let's say you're not aware of, right, any connection, and you just go through the definition, then this will be the sum, right, of k from 0 to n of k times the probability x equals to k, which is n choose k, p to k, 1 minus p to n minus k. And as you can note, right, this is a quite complex expression, right? It's a sum. Well, what can we do with it? It's correct, but it's not very useful, right, to work with, let's say. Not very easy to work with. But of course, right, we know that this must be n times p. And so how's that true? Well, right, if you represent x as a sum of xi, where xi are IID Bernoulli, right? Then expectation of x is a sum of expectation of xi, and the Bernoulli has expectation p, so that's just n times p. Okay, so the difference, right, is this approach is by definition of expectation, right? While the second approach is by representing x as a sum, right, of simpler random variables. And right, I hope you can see, right, the sort of the virtue, right, of the second approach, that it makes the calculation much simpler. And that's the whole point of us emphasizing this, right? When it comes to variance, right, it's the same thing, and it's even more complex because variance of x, right, if you go through the definition, then you have to go with expectation of x squared minus this. And right, this will be quite complex in terms of the sum, right, the formula. It is probably not easy to work with. But if you go through so that's by definition, right? But if you go through this representation of as a sum of random variables, and again, right, these are independent. So what we said above, right, works. Therefore, right, variance of x being the sum of variance of xi, right, will just be sum of p1 minus p and p1 minus p, like that. All right. Any question? Okay. So then let us continue, right, with the lecture, right? So we mentioned, right, so Bernoulli, the binomial, right? We look at the multinomial, right? We looked at a problem with conditional multinomial distribution. We skip this in the sense that I don't discuss this. The reason is I don't think the hypergeometric shows up too often in the context we'll be dealing with. And that doesn't mean that you don't need to know this or we won't quote this, right? We might quote this at some point. It's covered, right, in a standard probability course. So you just kind of review it, right? But on your own. The geometric, right? So the geometric models, right, the time, right, the first time, right, you get the success, right, the time you wait, right, the first time you see a first success, the time you see the first success in a sequence of IID trials. In this distribution, right, expectation variance. The negative binomial, right, would generalize the geometric by, instead of waiting for the first success, you wait for the first k successes, right? And both of these, right, have the one thing in common, which is, right, the last trial must be a success, right? Which gives a clue on how you would write their distribution function by placing, right, the previous ones as failure or success, right, accordingly. And the key, right, observation is that the negative binomial is a sum, right? The way we define it is a sum of the geometric. Therefore, right, independent geometric. Therefore, right, expectation and variance of the negative binomial is very easy to find, right, using the knowledge about the geometric distribution. Okay, so this is where we were last time, right? Any question about this? All right. So let me make sure on the problem set. I think so. This is Poisson. Yeah. Okay. So let's cover the Poisson next. All right. So the next one, right, which is super important, when we look at like queuing theory, right, our Poisson process is the Poisson random variable. Okay. So first of all, right, the Poisson random variable just takes on this distribution, right, where the value it can take starts from 0, 1, 2, etc. Right. So compared to the geometric, okay, compared to the geometric, notice that the geometric starts at 1. Okay. The geometric doesn't start at 0. Both of them have infinitely many values, but the geometric starts at 1, right? Why? Because you need at least one trial, right, to have the first success. From that same point of view, right, the negative binomial starts at k, right? Again, takes on infinitely many values, but starts at k. Why? Simple, right? Because you have to have at least k trials before you see k successes. Well, what does the Poisson model that allows it to take on value 0, right? It models a number of occurrences, right, of a type of an event with rate of, right, occurrence being lambda, right? Lambda being the parameter of the Poisson, and, right, is exactly the rate of like the event happening within a unit of time, right? So, for example, right, lambda can represent the number of customer, the average, okay, the expected number of customers arriving in the store within 1 hour, the number of earthquake, the average, right, number of earthquakes in a month, or the number of typos, the average number of typos on a page, right? So distinguish, right, again, X is the actual number of events, right, in the time window, while lambda, right, which is random, right? Or lambda, right, is the rate, or lambda is the average, right? Right, so this is the rate, okay. And the reason, sorry, and so that's why, right, a Poisson random variable can take on value 0, because, right, you within like 1 hour you could have no customer, right, arriving. And so, right, so the Poisson has expectation equal to lambda, right? This is kind of connected to the fact that, right, lambda being the average number of arrival within the unit hour. But the variance, right, of a Poisson is also lambda, okay? And so the question whether you can verify this sort of refers to different aspects, right, as you'll see. But basically, if you write down the sum, right, like this, right, if you write down the sum, right, k e to minus lambda, lambda to k over k factorial, where you sum k from 0 to infinity, you will get lambda. But this is rather, let's say, you need to know a trick or two, right, to handle that infinite sum. But there's a different way to relate, right, the Poisson to the binomial, okay? That will reveal, basically, why this is true at a more intuitive level. So the Poisson, right, distribution is the limiting distribution of a binomial as well. Limiting, okay, distribution of a binomial. Okay, as n goes to infinity, p goes to 0 in such a way that n times p goes to lambda. And so I think I might have a slide at the end of this lecture to discuss this, but I'm just going to tell you here, right? Basically, you see, because p goes to 0, this is why usually, right, the event that Poisson models are considered rare event. I mean, rare as in like, it comes from the limiting distribution of a binomial distribution, right? I mean, customers arriving in a store is not really rare. But I guess if you look at how to say this, right? If you look at all the customers at the mall, right, and look at the rate of them coming into a particular store, then that's quite small, right? And then if you average over all those customers and you get the average number of customers coming to that store, that's from that point of view, right? And so here, right, if you look at this binomial, right, then the expectation of the binomial is n times p. And because n times p goes to lambda, that's why expectation of the Poisson is lambda. The variance, right, of the binomial is np1 minus p, right? But notice that as n times p goes to lambda and p goes to 0, right? Then 1 minus p goes to 1. That's why this whole expression also goes to lambda. And that's why, right, the expectation and the variance of the Poisson are both lambda, right? So the Poisson and the Poisson being the limiting distribution of a binomial is actually an important theme, right? In some contexts, I think we may not have this so much in this class, but it's good to know, right? Or it might show up later on. I don't think so, but it's good to know. Oh, well, I was just talking about that part right here, right? But basically, right, distinguish this from a different concept that's also very popular called the central limit theorem, okay? The central limit theorem will give you the normal approximation of a binomial. But the normal approximation of binomial only let the number of trials goes to infinity, but the success rate usually is fixed. It doesn't go to 0, right? So the normal approximation of a binomial is a limiting distribution, but from a different point of view. Yeah, so just a quick mentioning here, right? We looked at the hat problem, I think in homework 1, right? And this is the expression, right, that we came up with for probability, right? That no one gets the right hat. If you take this expression and you push n to infinity, this actually goes to e to minus 1, right? Which is e to lambda to the k over k factorial, which is, is really just a fancy way to write e to minus 1. But it coincides, right, with the probability of a Poisson 1 distribution taking on value 0, okay? And in fact, right, this is true, that if you let x in the hat problem, right, represents the number of men getting the right hat, then the distribution of x will asymptotically approach the Poisson distribution with rate 1, with average 1, okay? But this is not a binomial approximation because the interaction of the people, right, they are not independent. So this is just a fun kind of connection from the hat problem to a Poisson distribution. But this is not the binomial asymptotic distribution that we just mentioned in the previous slide.
Make the chicken juicy like your lips. We all know your lips are not juicy. मुंह धुल जाके जब चिकन बन जाएगा तो उसको निकालें, उसी पैन में बटर डालें, गार्लिक डालें, दूध एंड क्रीम और
I think someone is not muting the microphone.
चार मसाले जाएंगे और इसको थिक करने के लिए इसमें पास्ता वाटर डालना है। लेकिन अगर आप मेरी तरह बहुत सियाने हैं, आपको डालना भूल जाएंगे, उसको पका पका के आपका बाल उतर आएगा। खैर, पहले दानिया शीट को अच्छे से क्रीम से मसाज कर दें। इसमें चिकन जाएगा, चीज मैंने मोज़रेला इस्तेमाल की है। रोल इट अप नाइसली, बेस पे सॉस लगाएं, इसको अच्छे से बेक करें एंड 1 मिनट, here you have it. मैंने ऊपर भी चीज डाली थी। They were super creamy, very flavorful.
Sehar, you forgot to mute your phone. All right. So let's take a look at problem. Okay, so this is a problem that, as mentioned in the title, right, would demonstrate the Poisson distribution, the geometric, right, distribution, and the binomial distribution together in one problem, right? So I'll let you read this problem, and then we're gonna see if there's any input to the solution. Okay. So first of all, right, just a comment on the language, right, of the problem, right? This kind of language, even though they don't, right, state explicitly, is exactly, right, asking you to deal with a Poisson distribution, okay? Because they give you a rate and they give you, right, the actual number of events. So this is like P right here, right? P is 1 over 100,000, and this is N, right? So if we let, right, X be the number of people hit by lightning, not lightning, right, lightning. Then what distribution does X have here?
Poisson with lambda equal 4.
Correct, right, Poisson 4. Good, right? And so the first one is just probability that X is bigger than or equal to 8, right? And so, I mean, that once you recognize that, then there's nothing much going on here. But we will, right, just remark that instead of summing this from 8 to infinity, let's say, right, just from a computational point of view, it's actually easier to subtract from 0 to 7. You know, again, right, when you write it down on paper, it makes no difference. But when you actually do the computation, right, one of them requires you to do 7 computations, while the other one requires you to do infinitely many, right? Even if you ask the computer to do so, right, it's better just to do the smaller side. So here, right, we're just gonna e to the minus lambda, which is e to the minus 4, right? 4 to the k of k factorial. All right. Any question about part A? Okay. So now part B, right? Read the language very carefully, right? Part B doesn't talk about, right? I don't know, number of people, but it talks about time. So how is part B connected to this whole thing? Or right, what exactly are we looking at in part B?
Are we looking at a binomial?
Very good, right? Exactly. So again, the point here is that, you know, I mentioned, right? You can do a probability question and there's a time dimension in it, and you can still do it with probability, right? This is another example. So the whole point is like, you know, depends on how you see it, right? You kind of deal with a stochastic process-ish, even while you do probability, right? That's why we spend time doing these kind of things. But yeah, right? So here, right, if you look at, right, so here, right, we're looking at 1 year, right? So if you look at basically Y, right, is a number of months in the year, right, where you have more than 8 people, right, hit by lightning, then Y will be a binomial, right? Of course, with 12 trials, because there are 12 months in a year. And the success probability, right, P is exactly this one right here, right? The one that we found in part A. Okay. And so, right, what we're looking at is just basically at least 2 months, right? So probability Y bigger than or equal to 2, which again, right, I guess just easier to do 1 minus, right? So N choose K, sorry, 12 choose K, right? P to K, 1 minus P to the 12 minus K. Again, right, what P is this number right here. Okay, any question about part B? All right, so let's look at C. Again, right, C, the question it asks deal with time, right? So why or how, right? How will we answer part C?
That one would be geometric, right?
That's correct, right? Exactly. Because here, right, the month is discrete, right? You're just basically waiting, right, for the first success. Well, success here, right, being the people getting hit by lightning, number of people get hit by lightning, right? The first month, right? That you have bigger equal to 8, right? Because again, right, the geometric takes on exactly that value, 1, 2, etc. And so then Z will be a geometric P, right? So what are we asking? We're asking the probability the first month will be month number I, right? So they're just really asking for probability equals to I, right? Abstractly. So that's 1 minus P raised to I minus 1 times P, right? From the geometric distribution. Okay. As far as like what assumptions we're making, well, the assumptions that we've been making throughout in part B and part C, right, is that the events of each month are independent, right? So the number of people who get hit by lightning from in each month are independent. So yeah, right, we make that assumption in this calculation. Right. Any question about this problem? All right, very good. So next one we'll go into, right, a uniform distribution. So which is basically, right, a continuous distribution type of thing. Sorry, looking for. Right. So right. So the ones, right, we've been going through so far are discrete random variables, right? So discrete random variables have mass function, right? Which means that the probability, right, if they're discrete, then probably it takes on some values, right? It's something, right? Which is not positive, right? As long as you stay within the support, right, of the random variable. The continuous random variable, right, actually, right, has a different characteristic, right? exactly for a continuous random variable, right? Probably it takes on some particular value, it's 0, right? Any particular value actually, right? Whether it's in the support or not. And so, right, with the continuous random variable, what we use to describe it is called the density, right? Density function, right? And we also have the CDF idea, right? Which again, we may or may not drag in here, but basically the notion of density, which is PDF, and the cumulative distribution function, right, are important here for continuous random variable. Okay. And so I guess the simplest, right, uniform distribution is the simplest continuous distribution, right, is a uniform random variable. Okay. Basically the one with constant, right, density, right, between two numbers. So it basically says that, right, the likelihood, right, is constant within these two values, right? And so that's why it's called uniform, right? And so this is expectation, this is variance, right? I mean, you can just find it by integrate, right? If you integrate, for example, from A to B, right, x 1 over b minus a dx, you will get b plus a over 2, right? That's the formula for expectation. For the variance, you have to do this with x squared, and then you subtract this, right, squared, the formula expectation x squared minus square expectation, you'll get that. But yeah, right, so that's the uniform. What does a uniform model, right? So when it comes to continuous distribution, unless we talk about the normal distribution, right? A common, let's say, model, right? That kind of a common object that continuous random variable models is time, because you think of time has that kind of right continuum that we intuitively right think about when we look at continuous random variable. But of course, right, because different continuous random variable have different characteristics, right? So what time, right, you use to model this has to be carefully chosen, because you cannot just say, right, I will model any kind of time as a uniform, or you cannot just say I will model any kind of time, right, as an exponential, right, things like that. So what characteristic of a uniform, right, that we need to pay attention to? Well, of course, right, two characteristics. That means it stays within two definite bounds, right, A to B, right, and then its tendency, right, doesn't change throughout that. So for that reason, usually something like bus arrival time, right, or train arrival time, whatever, tends to be modeled by uniform. I'm not saying has to, because you kind of know roughly, right? You know that, like, let's say a bus has to arrive between, this and 10 minutes later, that kind of thing, right? Of course, the bus can be later than that, right? But suppose it's guaranteed, right? And then within that time window, you have no idea if the bus will arrive within, right? It could arrive anytime between those 0 to 10 minutes. Then it's a uniform, right? But of course, right, in contrast, I'm just gonna kind of like, peek ahead, right? The exponential, right, has this kind of shape. So you see, right, two things. The exponential has no upper bound. So there's no kind of like definite kind of point where you say the event must be arriving right before that time, right? The exponential just keep on going forever. But it also exhibits a decaying, right, kind of property, meaning that, right, the density of the event, the time closer to 0 is higher, right, than the density far out. So things like that. So again, right, no right or wrong answer when it comes to modeling, but it's more like, does this capture, right, the phenomenon we have in mind? So, but that's kind of like what the uniform is used for, right? We don't see the uniform so much in this class either, I don't think, even though uniform is a very, very popular random variable, right? Because we deal with, horizontal process and Markov chain, right? Both are discrete, in that sense, but it's still good to kind of go over this a little bit. So, all right. So this is a question, right? About a uniform distribution. So again, I'll give it a minute or two and then see if any input about this question.
I think A should be 1/3 because
Right. I think you're right. Let's just draw a picture first, right? So what are we looking at here, right? What's uniform? What's uniform in this problem, right? In contrast to what I was telling you in the slides, is the passenger, right, arriving uniformly, okay? Well, but whatever, right? What's uniform is the passenger's arrival time. So we have something like from 7 to 8, right? The passenger will arrive uniformly, right? Within this time window. And then, right, within this time window, what happens is we have train, right, that arrives, or, yeah, right. Basically, train. So the train here, funnily enough, are supposed to kind of like arrive at an exact time, right, and then move on immediately. So that's the thing, right? And we're asked, right, basically, where the passenger ends up if they just, arrive kind of randomly, right? And then hop onto the first train that arrives at the station. Again, a very kind of weird scenario, but right, we just have to interpret it and see how we answer the question. All right, so whoever said the answer is 1/3, what's your reasoning?
I actually think I had it backwards. I think it's 2/3.
Okay, yeah.
Reasoning being that if it's uniformly distributed, you can break it up into 4 time blocks of 15-minute intervals. So if the train, considering it's uniform, if the guy arrives between 7 and 7, like in the first 5 minutes, then go to destination B because the next train that's going to arrive is train B. But if he goes at 10 and or the 5 and the 15, then the next
So B is 7:05, right? And then 7:20, right?
yes.
And then 35. And then the next one will be 50, right?
So if he gets there at 7, he's going to go to B.
Correct, right? So where would he end up being at B? He will end up being at B here, right? First of all, and where else? Oh, and I guess let's mark in A, right? Just for clarity. A will be
15, 30, 45.
right. A will be 15, right? And then 30, and then 45, and then also here, right? But so okay. So the intervals for B will be here, right? And let's just, for those who don't see it, right? If he arrives within this 2 interval, he will go to A, right? Correct?
Yeah.
So yeah, right. So the intervals for B will be this. Once we recognize that, then this, and then this, and then this, right? Correct? And then it's going to be, because it's uniform, it'll be the ratio, right, of the length of these intervals over 60, right?
Correct.
And the answer will be,
If you directly add up the time,
yeah. So the answer will be,
it would be 40 over 60, which is 2/3.
Correct. Yeah. Oh, sorry. I guess so. Sorry, for some reason, right? It has to go to A, so I'm doing B. So yeah, A is the other one. Sorry, right? Yeah, but correct. You should add up the other intervals. I was highlighting the wrong interval, but anyway, right? Yeah, good. Any questions? That part. Okay. So what about part B? So I hope you see that part B is very similar to part A, right? You just shift the picture 10 minutes right to the right. Okay. And if you do that and you draw the picture, you'll see that the answer actually still is 40/60. But I think there's some kind of slight different intervals you have to take into account. But yeah, right, the logic will be the same. I won't draw the picture here, right? You can do it yourself, but okay. Any question? Okay. I think there's another question here, right? This is another question. Also dealing with uniform distribution. So again, right, I'll let you read it and then we're gonna discuss it. All right. So this one is, I guess, a little bit more sophisticated, right? Because, so first of all, right, the language here, that a point, right, is chosen randomly, okay, on a line segment. So the first thing it wants to tell you is that, right, if you say you do something randomly without any further qualification, then the default, right, interpretation is that that's a uniform choice. Is that okay? If you do something randomly, if you don't say whatever, then it's a uniform distribution. So what it's saying, right, is that you have a line, right, from 0 to L, right, and you pick a point, let's say uniformly, right, between, along this line, right, line segment. Of course, right, that point will break the line into a longer segment, right, and a shorter segment. And we're asked to find the probability that, right, the shorter over a longer, right, is less than 1/4, I think. Right? But yeah, so how do we phrase this statement? So, right, so X here is a uniform, right, from 0 to L. But what does this probability have to do with X? So here, right, something that happens a lot in, this course, right, or in probability modeling, right, in general or whatever, right, stochastic process, is that you have to interpret the question back into whatever information that's given. So if you let R, right, let's say be in the ratio, right, that you want, of short over long, right? Then how is R related to X? Because X is really what's given, right?
R is equal to the min of x and L minus x over the max of x and L minus x?
Yeah,
That-
that's not wrong. That's not wrong, but that
Okay.
that would drag in the min and max expression, which, right, as you can see, dealing with in terms of random variable might make it right, not easy to tease out. You're right, but let's even make it simpler. When would the min happen between x and L minus x? You're right, that those are two expressions, right? When would the min happen? Okay,
When
we
x is
can
less
we-
than L divided by 2?
Right. So you see, that's the key, right? We can make that. Then, right, it will be clear to us, you know, what the ratio will be, right? Instead of having to deal with min and max. So if x is less than L over 2, then the ratio will be correct, because x will be the shorter segment. And when x is bigger, it will be
L minus x over x.
correct, right? And so then what we're asking, right, is the probability that are less than 1/4, right, or less than or equal to. Here it doesn't matter because it's a continuous random variable, right? So you see, right, again, might look scary, but it's just going to be, well, this will be less than or equal to 1/4 if x is less than L over 2 plus. Does that make sense? And the reason why we can break into a sum is because, right, these are
Disjoint
mutually
effect.
exclusive. Exactly. Yeah, disjoint is a good term too. I guess it's shorter than mutually exclusive, but correct, right? And well, is this scary? Not really, right? Let's handle, let's say, the first expression. Notice that this is positive, right, or non-negative, so I can multiply the expression, right, across. So this is this, correct? Which is what, 5x is less than or equal to L, or x less than or equal to L over 5, correct? And so, right, this will be equal to, for example, the first one as probability of x less than or equal to L over 5 and x less than or equal to L over 2, correct? Which is exactly what?
X less than or
L
equal.
over 5, right? And you can handle this one similarly. Is that okay? Any question on this? Right, so here's the full solution, but it's exactly what I just told you about. All right. So, any question?
So to compute the probability that x is less than or equal to L over 5, numerically, what would we do? We would integrate using the
You could,
Negative.
but right, notice that if we're in a uniform setup, right, that's what we are, then things will just become ratio, right? That's the easy calculation. So it's 1/5. You could integrate, right? You could integrate from 0 to L over 5 of 1 over L dx, and you exactly get 1/5. Or you can recognize this as a ratio, right? So the uniform is the continuous version of equally likely event in discrete distribution. So you can just ratio it out. But yeah, if you don't feel comfortable doing that, you can integrate. You'll get the same answer.
Okay, thank you.
Sure. All right, we're good. Okay. I think let us cover the exponential distribution real quick, and then I'll give you the quiz, and we'll look at the problem after we come back from the break. So, right, the exponential here, right? So the exponential distribution, I guess we can allude to this already, right? So first of all, right, it takes on positive value, right? Or if you want, right, the support here is from 0 to infinity, right? Unlike the uniform is an infinite support, right? Non-negative values only, right? No upper bound. And so expectation and variance of the exponentials like this. The y here has to do with, right? You just have to do an integration and integration by parts, okay, to get this. If we are in a probability class, I will go over the calculation right here. We'll skip that. But so what you want to pay attention to the exponential later on, right? We'll look at this when we move to the queuing model, which is in chapter 5, is how it's connected, right, to the Poisson process. So exponential and Poisson are closely connected. And also this explains why we model, right? Or we say the density of the exponential as this way. So basically, right, if you remember what I said about the customer arriving at the store, right? So if you look at the customer arriving at the store, right? And if you don't count the customer, but if you look at, let's say, right, the arrival time between customers, right? Then if the customer is arriving, right, as a Poisson lambda, now notice the Poisson lambda counts, right, the number of customers arriving. While if we look at the exponential, that will look at the inter-arrival time, right, the time between customers arriving. Then the connection is like that. And technically speaking, right, this is not really Poisson, but it's a Poisson process because now we're kind of moving things along in time, right? But so the one connection I want to make is that, right, notice the exponential expectation here is 1 over lambda, while the Poisson, right, expectation of it is lambda. Why? I just want to make this connection. The reason is very simple, right? The lambda in the Poisson expectation is 3 customers per hour, let's say. 3 events per something. Then of course, right, if 3 customers on average arrives per hour, then how long does it take for them to arrive on average between customers? And roughly speaking, right, it takes 1/3 of an hour for a customer to arrive. Correct? So that's exactly that 1 over lambda here. Okay. Real quick, you know what? Let's go to the quiz and then we'll go back to this. So for the quiz, let's do the lightning problem. Okay. So by the way, right, 3 parts. This is the quiz today. Today, right, going forward, your quiz will be graded on precision, meaning that if you make an error, you get points off, right? Mostly no points for whatever part. So do A, B, and C, right? You just have to write down the answers. You don't have to like kind of elaborate on the reasons. And submit, right, at before 10:35 or rather 11:35. Okay. Any question before we take a break? We continue at 35. All right, so I'll see you at 11:35. All right, let's continue. Is there any question before we continue? All right, so I guess we were talking about the exponential, right? And right, and I mentioned how the exponential, right? The relevance for it, and you see, right? This is why, like, even when we deal with like the Poisson process or queuing model, right? The exponential will show up a lot, and we'll talk even more in depth about exponential in that chapter. But the reason, right, is exactly right here, that very naturally, right, or well, I guess not naturally, but for mathematical reason, if you have Poisson arrivals, right, meaning that if you count the number of events using a Poisson random variable, then the inter-arrival time, right, the time between the events, will be an exponential random variable, right? It's actually a quite fascinating mathematical fact that can be proven, right? Obviously, that's not intuitive. I mean, obvious, right? The connection. But one, if you accept that, then there are certain things that would follow. For example, how the expectation of the Poisson and the expectation of an exponential, right, would be reciprocal of each other, right, from that point of view. Okay. Now, having said that, I just want to give a strong a caution, right? So yeah, I was talking about the inter-arrival time, and I was talking exactly that, right? So here's a strong caution, right? Is that if you look at the exponential, let's say casually on the internet, you may see it's defined like this, or you may see it's defined like this, okay? And it's one of those things where you blink and you miss it, because the difference, right, is small but crucial, right? And what's the difference? The difference, right, is that here is called exponential lambda, but here is 1 over lambda, okay? Well, if you note, right, here, I call exponential lambda, and I define it as lambda right here. Okay, what's right and what's wrong? It's nothing along that line, right? Clearly, let's say my exponential lambda is there, exponential 1 over lambda or whatever, right? Just to make things more confusing. And so, but let's kind of try to explain where this comes from, okay? So clearly, right, our motivation comes from the modeling, right? And then how we want, or how for us, the exponential, right, plays the role of the inter-arrival time in the Poisson process. And that's where the 1 over lambda, in terms of expectation, must come from. Notice the lambda in here will result in the expectation being 1 over lambda, right? Because of integration by parts, okay? While for this formulation, and noted, this is actually where you actually see it a lot in statistics course, right? Which of course is very popular these days. What they would want is they would want to land the exponential back on expectation being lambda. The reason is, this will make it convenient to estimate lambda, all right, by the sample average, like X bar, that kind of thing. If you use our formulation, then the estimation of lambda will become quite awkward. It'll become like 1 over X bar, and estimation with that and calculation with that is very awkward in statistics. All right, so I just want to make that remark, okay? Because again, right, it's probably obvious here these days in Asia, all of you guys are taking statistics or will be taking statistics, or you should have seen this way of writing the exponential. So I just want to make sure that, right, in our class, we write it the other way, right, for this reason. Okay. We can mention very quickly, right, that the exponential, right, has a so-called memoryless property, meaning, right, and we'll see this again, right, in the queuing model chapter. So here's the interpretation, right, that if you think of, right, the exponential random variable as modeling the time until an event has happened, right? And there are two typical scenarios for that. One is a waiting time, right? You wait for something to happen, like you wait in a line and you wait until you're served, right? Or you wait until you move to the next spot in your line. because the first person on the line has already moved to be served, things like that. That tends to be modeled by an exponential. Okay. Or another one is going to be the sort of like the expiration time or the breakdown time, right? The breakdown time of a machine, breakdown time of a human, meaning we die, right? Can also be modeled in exponential. But if you take the point of view of, let's say, the time for a let's say a machine, right, to break down, then the memory's property says this, right? If it has survived some time, t, right, it's the time of survival already, survival time, right? Survival history. Let's say 5 years, right? And this h is the extra arrival, the extra, right, survival, right, given, right? So in English, it's like, well, what's the probability that my iPad will survive the next 3 months, given that it has survived 5 years? And if right, this is an emphasis, if I use the exponential to model my iPad's lifetime, then the answer is, surprisingly, it's the same probability as if it were new, right? Because there's no history here. And clearly, right, this doesn't really, right, accord with, let's say, our intuition about breakdown time, right, of machines or lifetime of machines or human, things like that, right? Clearly, somehow we feel like, right, a new device should have, I guess, more chance of surviving, right, a time interval compared to when it's old. I don't know. That's at least my intuition. But what I'm saying is, like, this is actually the property of the exponential, meaning that if you use the exponential to model something, this is what you're committed to. All right. And if you don't want this to happen, or you don't think this is what your system exhibits, then you want to modify the exponential, right? So that's the thing, right? There's no right or wrong here. This is a property, right, that we must be aware of, or we should be aware of. And if it doesn't work for our model, then we need to change it, right, to capture whatever our model tries to say. One way to capture it is to use, like, the hazard rate, okay, which allows the rate to change as the random variable has survived a longer time period. But yeah, right. So maybe one last thing, right? Long story short, the reason why this is true is really because lambda here is constant. Sorry, right? Lambda here is constant, meaning that, right, the hazard rate in the exponential random variable is constant through, doesn't matter what x is, right? You can kind of, roughly speaking, if lambda here somehow depends on x, right? Of course, that's oversimplification because you have to really write it down correctly. But roughly speaking, if the rate of breakdown depends on where the random variable is, then you can kind of see that, right? The memoryless property won't hold, or it will have memory, right? But if lambda doesn't know where it is, doesn't depend on the actual value of the random variable, then it's memoryless. All right, any question about the exponential before we look at the problems? All right. So, okay. So here, right, is the first question. And just a remark, I'll let you read it. But here, right, it's really a problem that it's not meant to demonstrate the exponential in its time aspect, but it's kind of meant to do another kind of task, which is optimization, right? But yeah, so, but still, it kind of works with the exponential distribution a little bit. So, and it kind of teases out a concept of, as you see, the median here. Okay, but I'll let you take a look and we'll discuss. Okay, so let's first draw a picture here, right, to demonstrate the problem. So there's a road of infinite length, right? So this is the road, right? And accident occurs, right? Fire occurs anywhere, right, on this road, but the distribution of the fire, right, is exponentially distributed, right? Again, sounds kind of artificial and made up, right? Okay, whatever. But notice that if we take this a little bit seriously, right, meaning that if this is true, then there's an implication here, right? The implication is the fire, right? Because the density of the exponential is like this, right? The fire is likely to happen, right? More likely to happen closer to zero, right? Compared to far off places. Okay, but that's what this model means, whether it's true or not, whatever, right? But anyway, right, there's a fire happening randomly on the road. Now you will put a fire station, which is a static, right, location somewhere along the road, right? And of course, when you put a fire station there, right, what do you want? You want to optimize, right, the distance to the fire, right, so that you can do fire rescue and stuff. And but of course, right here, optimization, in the stochastic context, can only optimize on average, right? Of course, that's not the end of the story, right? But here, right, let's say if you let X be the location, right, of the fire, then clearly, right, the absolute value is the distance away, right, from the uh, uh, fire station. So the average distance, right, is this quantity right here, right? And that's why, what do we want? We want to minimize, right, over all choice of A of this quantity, right? So that's the setup of this question. So it's really optimization, right, in the stochastic context, but a very simple problem at that. Any questions so far? And so, right, what's the next step? Well, the next step, right, is going to be to write down this expression, right? So this will be the integral over 0 to infinity of x minus a absolute value, right? Eta minus lambda eta minus lambda x dx. Okay, so you minimize over all a this expression. Okay, so maybe this is where maybe we can ask some question to you, right? What would be the next sensible thing to do here, given that we've written this so far? What would the next step be? What should we do next?
Because we have the absolute value, should we split the integral along?
Excellent, right? Exactly. We should handle the absolute value first as a technicality, right? Correct. Because exactly, right, from now on, from this point on, it's only technicality. So yeah, we should split the absolute value, right? So of course it's 0 to a, right? And then if it's 0 to a, then it's a minus x. And then a to infinity, in which case it'll be x minus a. Very good. All right. Then what next? Throw the whole thing to ChatGPT and pray for the right answer. That's what we do here.
Do we integrate by parts?
Yeah. I mean, so the thing, right, is you would have to, in theory, right, evaluate this expression. But let's say if you can evaluate it, right, using indication by parts and whatever good techniques you have, then what else do you do? Then what next? Is that it? After we evaluate that integral, what do we do? Let's say we have an expression, right?
Sure.
Then what? Say again?
I just said I'm not sure. Let me think about it.
Sure. First of all, right, try to visualize, right? After you integrate that expression, right, what do you have? What kind of expression would it be?
We integrated the PDF, right?
Dx, correct. We integrate, not the PDF, right? I mean, PDF is only this part, right? The PDF, to be clear, is this part. We integrate the whole expression, but yeah, I mean, the PDF is involved for sure. We integrate with respect to X, if that's what you're asking. Yeah, we integrate with respect to X.
Right.
Yeah.
Okay. Normally, if you integrate the PDF, you get a CDF.
No. So again, right, that's not the case here, right? Because
Well,
this is
yeah,
not the PDF.
it's not. Yeah.
So no, right, and you're not thinking in the right direction. This is not about the story about CDF or PDF, that kind of thing,
Okay.
right? So the point is, after you integrate this with respect to X, what's remained? Lambda remains, which is clear, right? Because lambda is the parameter of the model. And what else remains?
Variable A.
Correct, right? Because A represents your choice of, right, location for the fire station. All right. So it's going to be a function of A and lambda, right? Lambda being a constant, forget about it. But A is our choice here, right? And when I want to minimize with respect to A, so what do?
Oh, take the derivative, like in a calculus context.
Exactly. That's it, right? Exactly. After you evaluate, you will differentiate with respect to A, and then?
Set equal to 0, and then solve for A.
Perfect, right? That's it. So you see, what I want you to see, right, all of you, is sure, right, this problem can be tedious, okay, in terms of the technicality, but the picture or the proceedings are quite clear. Those are the steps, right? These are the algos. In between, if you feel lazy, you want to do integration by parts, as you know, your friend pointed out, throw it to machine, fine, right? That's what the machine can do for you. But if you throw the whole thing to the machine and pray for the right answer, I think that's too much. Okay, especially in the context of, like I said, I'm commenting on, you know, the pervasiveness of AI these days, right? The reason is, again, I'm not saying that ChatGPT cannot get this answer right. Very likely it can, but it may get wrong as well. It might make a wrong step here and there, right? It does happen. Okay, I've seen that, not in this context, but in some other. And you're not very well aware of your context, then that's you know, that's irresponsible, right? But if you're, you know, the steps and you only, right, let it handle the mechanical steps, I don't see what's wrong with that, right? Of course, I mean, in a class like this, you're supposed to know integration by parts as well. But right, but I just want to say that the steps are very clear. Now let's handle the integration by parts, right, thing. Now, of course, right, you could integrate by parts here, right? That's an option, and it's not too bad, but it's, let's say, painful. So the solution, right, I'm providing for you. Whoops. Oh, somehow the solution is down here. I have to swap the, sorry, right? It should be here, but anyway, the solution I provide for you here, right? Exactly is this thing, is to use a, let's say, a more sophisticated calculus tool called the Newton-Leibniz formula. All right, you can look at it on Wikipedia. But basically, it's just a more sophisticated version of the fundamental theorem of calculus, because you have A here, right? The reason why we need to use Newton's Leibniz rule is because, you know, basically the A also happens inside, right? And Newton-Leibniz rule is like this. You can look it up on, so Wikipedia, right? But it says that if you want to differentiate with respect to A of an integral, right, like this. So notice right here, a appears on the limit of integration and a appears inside the integrand. That's why it's a new thing rather than fundamental theorem of calculus. Then it's going to be right a combination of both rules. You apply the fundamental theorem of calculus to plug a right the upper limit into the x argument, and also you move the into the differentiation inside like that. Okay, so that's how you differentiate. So you don't have to integrate all out and then differentiate. Notice, right, it's helpful because here, if you plug a into x here, you get 0. That's why you only have to move the integral inside and you will get, you know, that. So that's the only technicality piece that I want to tell you, right? But the rest, the steps, like I said, should be straightforward. All right, any question?
Quick question. I've seen this before, the Newton-Leibniz rule. I forgot the exact reasoning, but isn't there some convergence criterion that allows us to move the derivative, the partial derivative?
Yeah, that question is very sophisticated. Yes and no, in this way. As the structure of Newton-Leibniz goes, it goes like that. The question whether we can move the differentiation inside the integration is a separate question that's always posed if you want to move it inside. You understand what I'm trying to say? So what I'm saying is like your question is valid and very good, but in the context that if we can do it, then it will follow like this. Does that make sense? So, but the question is if we can do it or not, can we move it in or not? It's a separate question. The answer is well, you only see tricky things like that in a real analysis class, for example. If you handle like continuous function or, you know, let's say nice function, you can always move it in. But to give you like even a more, let's say, rigorous question, right? The answer is you can move it in if, you know, since you asked this question, maybe you know this idea, but it's called L1 function, meaning that if you have this is finite, I think, then you're fine. Or yeah, at least over some interval a. So for some a in interval of some interval that you need, things like that. But so you see, of course, right? The integral we're dealing with is very nice. So no worries about that, right? Yeah.
Okay, thank you so much.
Sure. All right, any other question? All right, so let's take a look at the next exponential random variable question. So yeah, this one is a more conventional question. So maybe this one should be asked first, but it doesn't matter. Okay, so nothing really going on here with this problem, so I'm just going to show the solution. Okay, it's really just a calculation, and here I did use the the notation for the CDF, right? Doesn't really matter. It's just really an integral. The integral from 2 to infinity of e to minus 1/2 x 1/2 dx, and I kind of invoking the fact that sorry. Yeah, I was invoking the fact that the CDF of an exponential is e to the minus, so the CDF of an exponential has the form e to the minus lambda x. Hold on, one, yeah, this is a CDF, but this is 1 minus the CDF, so that's why. But it doesn't matter if you integrate this, you get that. The second one, right, is that here, right, is the conditional probability, right? So notice that this exactly is the invoking the memoryless property that we mentioned before. Of course, you can do this, right, using the definition of conditional probability, and you'll get exactly the same answer. But you'll get some cancellation, right? Here, we just move directly to the memoryless property to make our calculation easier. But basically, right, whatever you do, this question is not too hard. You just apply the good old definition and you get what I got here. Okay. Any question about this problem?
I'm sorry, you probably addressed this, but why is like that first step there, P of x greater than 2 goes to 1 minus f of 2?
So by f here, I mean the CDF, right? F here is my notation for the CDF of an exponential. And again, this whole thing is totally unnecessary. It's just, I guess, at that moment, I felt like doing that way. You don't have to. The point is you just integrate this straightforwardly, right, like this. But the story is that f, like I said, or f sub x represents usually, or not usually, always, the so-called CDF of a random variable x, all right? And what does it mean? This represents the probability that x is less than or equal to little x, all right? This is the definition of a CDF. And as you can see then, right, then probably x bigger than 2 is 1 minus probably x less than or equal to 2. Does it make sense? Yeah, and the only reason I did that is somehow at that moment I quote the known fact that the CDF of exponential is like that, but you don't have to know it, right? I mean, you can just integrate that. All right. So I believe the next one, right, is the normal, which should be the last one. Sorry, let me check. Right. So, right. So the normal random variable, okay. So the normal random variable, right, is, well, right, no need to advertise it. One of the most, I don't want to say important, that's probably the wrong word to say, one of the most ubiquitous, right, random variable in probability statistics, period, right? I guess the question to ask is why, right? Rather than, whatever. So first of all, though, right, we want to kind of define, right, the normal. So the normal would mean mu and variance sigma squared, right? Notice this is the variance, right? Not the standard deviation. So I think some tradition somewhere quote the normal would mean n standard deviation. But I think from where I came from and most textbooks I read, right, they always quote the normal with mean and variance. So, right, so just careful when people say normal 1/4, right? That means sigma square equals to 4, right? Sigma equals to 2, right? It's just a thing. And so, right, this is the PDF. And right, of course, that's a well-known right bell curve with right center around mu, right, and spread roughly sigma, right? Okay. So, well, the normal, right, shows up in many places. For us, for our class, it'll show up in the last chapter of the class, right? Which we'll get there hopefully. Is the Brownian motion chapter, right? But of course, right, it shows up in many other places, like the noise terms, right, in regression, right? And well, noise term in regression, I guess, in many other places. Wherever, right, you have an error terms is very common to start modeling, right, the error as a normal term, right, a normal random variable. But right, I guess the reason why it's ubiquitous is because of the central limit theorem. In fact, right, this, if you kind of know where it comes from, this helps explain why the error term or the noise term is usually modeled as the normal distribution, okay? The reason is, right, here. right? Basically, this looks like a mouthful, but all it's saying, right, is that it's some kind of this is the sum, right? This is a standardized sum, right? This is a standardized version, right, of the random variable. If you standardize, right, IID random variable, and then scale it correctly, right? Because notice, right, if you scale with 1 over n, then you will end up being inside 1 over root n, then you end up in the territory of the law of large number, right? In which case you will land on the expectation rather than, which is a number, right? Rather than a distribution. But the message here, right? And notice, right, if you cover this scaling, then this looks like, or this is, right, like a random walk, or, you know, basically you're averaging, right, random variables, okay? You average ID random variables in a with the right scale, of course, right? But intuitively, this is why errors, right, or noise usually modeled as normal, right, distribution. Because noise, if you think where noise comes from, right, or error comes from, they comes from the average effect, right, of different pull and push in different directions, right? So the noise comes from, you know, different measurement errors that are independent of each other, and, you know, average out, right, over different trials, things like that. So whenever you have that averaging effect of ID random variables, right, central limit theorem tells you that you have a normal distribution, right, waiting for you. And that's why people just go into it and say, well, you know, then let me just model my noise as normal. But as you can see, right, again, just a comment, right, there's a danger in that, because if the assumption of the central limit theorem is not satisfied, where most notoriously the independent assumption, right? Because interaction, right, that leads to the noise may not be independent, who knows, right? But if they're not independent, then the result may or may not be a normal distribution. So again, talking about the appropriateness, right, of the model here. Again, conventionally, and also for many good reasons, right? Mostly like the ease to work with the model or the beauty of the model, normal distribution is used, but it doesn't have to be, right, the right tool or the one that would capture the phenomenon you want. Anyway, right? So, but as far as we're concerned, right, central limit theorem will be sort of like, you know, sort of like the backbone of many things in probability. In fact, it's also the bridge, right, from discrete to continuous distribution. Because here, right, notice that no assumption is made on the xi's. So of course, right, if xi's are continuous, it also, right, sum up on average to a normal distribution and average out to a normal distribution. But discrete also works in the same way. And that's actually the amazing thing, right? Because you have discrete random variables that average out to be, right, approximable by a continuous distribution. And that's where, right, normal distribution used to shine historically. Because, right, for example, if you have binomial distribution, and remember, right, this is exactly it. Again, where we want to see the binomial as a sum. It's a sum of what? It's a sum of IID Bernoulli, right? And that's why the binomial is prime, right, to be approximated by a normal distribution. And the point, right, is that if you have a binomial distribution with a very high n, right? Exactly, you know, high n is exactly like n goes to infinity, right? Well, how high is high, right? And the irony here is people recommend somehow 30 trials is enough to use the normal approximation, which is an irony in the sense that, like, no one thinks of 30 as infinity, right? And so again, right, it has to do with what kind of error are you willing to tolerate and things like that. Not a topic of this course, right? I'm just mentioning. But the point is, if you have a high n, and let's say for us, high here is, let's say, around 1,000, right? Then if you want to calculate, right, the distribution of this binomial, for example, if you want to look at the binomial, let's say 1,000, 1/2, right, is between, let's say, 498 and 502, right? If you just think about this for a little bit, it will involve expression like 1,000 choose k, right? Where k is around 500. And if you, right, have ever played with that number, you see that it's a humongous number, right? It's huge. I think computer these days can handle that big number, but used to be, right, that would be an overflow. right? And in the 18th century, clearly, right, nothing can really handle that numerically. And then you have 1/2 raised to k. And again, right, you have a humongous number here and you have a very small number there. So, right, the calculation error is just really, right, waiting to happen. And so, right, instead of committing those kind of errors, right, if we move to the normal approximation, right, notice here, you're subtracting the mean and you divide by the standard deviation, right? Exactly, that's a standardized version. So very easy to remember. Then, right, you can move to a standard normal context where, right, instead of dealing with the combinatorics, you can just use integration, right? Which, well, I guess will cause less error. So that's the only message. But of course, right, doesn't have to be only this, right? It works in general. Okay, so that's the normal distribution for us. Any question? All right. So I think, right, yeah, this is the last question for this problem set. Okay, so it has two questions really, right? This and this. So the first question, hopefully, right, is a standard question, right? Where X here is a binomial, what, 1,000, 1/6, correct? So I guess, sorry, I did not include this here, but should not be super important in this class. But in these things, right, you want to also be careful of, like, you know, how to say this, or include, right, the so-called continuum correction, right? Because you move from a discrete context to a continuous context. So what happens is you bump the upper bound by 0.5 and you reduce the lower bound by 0.5. Notice, right, from the discrete point of view, it doesn't change anything because X can only take integer value. Right, or I think it's continuous correction, not continuum correction, but it doesn't matter. All right, or is it continuum correction? Forgot, anyway. Right, and then, right, it's just gonna be straightforward because you will subtract, right, the mean and divide it by the standard deviation. And this is a standard normal. Like that, right? And then we just look up the normal table from there, right? The final answer is not important in this case. We just want to get to that form. Okay, any question here?
So in the last line,
Yeah.
it's kind of the form probability some constant A less than or equal to Z less than or equal to some constant B, correct? So could you rewrite that expression as probability Z less than or equal to B minus probability
Yeah,
Z less than or
so
equal
yeah,
to A?
so correct. I mean, in fact, right, this notation, what you said is absolutely correct.
Okay.
They use
Wait.
a CF notation like that. Yeah, correct.
Oh, okay,
Absolutely
You're
correct.
using the CDF notation, okay.
Yeah. No, I mean, not everyone use the n of something as CF of normal. I'm quoting financial math, Black-Scholes context here, but I'm just confirming what you said. Yeah, absolutely.
Oh, okay, thank you.
Yeah, this notation is not universal. but in math finance, people use this. But I mean, as far as this class is concerned, I don't care to move down here because it doesn't serve anything, right? The step up here is the same thing because we're not getting down to a numerical value by hand. All we can do is like plug into a computer and ask what that number is. Okay, but let's focus on question B, right? Really is the main question here, and this has the flavor, right, that is connected to this class in terms of conditional thinking, right? So let's see. And we discussed this kind of flavor of the question before. So how would we handle B?
Maybe like a binomial of like 800 and 1/5.
Excellent, exactly, right? So that what you said is perfect on own count, right? So basically here, the number of 6 has appeared 600 times, 200 times, and so if, right, so this is conditioning, right? But now if we condition on 6 appear 200 times, right, you want to find the probability that 5 is less than or equal to 150, right? So notice that, right, you can't really use the central limit theorem directly to this expression, okay? Because I don't know, right? Central limit theorem doesn't have a conditional version. So you could, write it down by definition, but if you write it down by definition, again, you'll see that central limit theorem doesn't really apply to that version either. So the way out here is exactly use conditional thinking, and I hope you recognize that it's exactly of this flavor, right? Where we're on top of 5 and 6, but that's exactly right. The number of outcomes, or the number of types here, right, are 6 types, right, 1 to 6, and we condition on 6 as having happened, right? And so that's it. That will reduce, right, the number of trials into 800, right, because it's going to be, right, 1000 minus 200, and the success probability now, right, of 5, right, will be, well, now because 6 is already out, correct? Then you only have 5 numbers left, which are equally likely. So that's going to be 1/5. So that's exactly probability of a binomial. 800, 1/5 is less than or equal to 150. And from here, right, this one we can use central limit theorem on with continuum correction and things like that. Is that okay? So let's show you, I guess, the answer, right? But all right, any question?
Could you I'm sorry, I'm still a little bit confused. So we condition on the fact that 6 appears 200 times. How does that make the fact that 5 appears less than 150 times follow a binomial distribution with p equal 1/5?
So again, right, actually, it's exactly a part of a concrete example of this. But so here's the thing, right? For example, so first of all, right, you think about it. You have really, right, the dice. So you have 6 types here, correct? You have 6 types that can, but you really hone in on only the number 6. But so you throw 1,000 times, right? And so notice it's exactly a multinomial, really, right? 1,000 times where, right, all numbers can be any type from 1 to 6. Agree? Now right? You conditioned on 6 has appeared 200 times. So again, right, like the blood type example that we talked about last time, right? So, but if 6 appears 200 times, that's a fact, right? Then you look at the remaining one where that's where your question is, right? Then clearly, right, first of all, there are 800 trials left, right? That are the random part. And these 800 trials can only take values from where to where? From 1 to 5, correct? Because 6 cannot appear in these 800 trials.
Was that given to us in the problem that 6 cannot appear?
It's sort of like by language, because condition on 6 appear 200 times, and you look at the remaining ones, right? It's just the language. You understand? Because you say 6 appears 200 times, so that's a 200 that has number 6. So if you look at the remaining ones, they cannot be 6 anymore, right?
Sure. Okay.
Right. So it's just by what we say, right? We look at the remaining ones, the ones that we don't know the result of. There cannot be a 6 in them.
Well,
Right?
that
They can only
makes
be
sense. Okay, the all 1,000 trials were performed. We just know the knowledge of this number of times that 6 appeared, and it's not 200 consecutively. It's
no,
200.
no, nothing, no, exactly, no,
Well, that makes
nothing
so much
about,
sense. Thank you.
no, nothing about, right, exactly, no, yeah, okay, if that's where your
Okay.
confusion is, yeah.
Oh, I understand. Okay.
Mhm. Right. Any other question? All right, very good. I think this is a right spot to stop. We have a couple more minutes, but it's not enough to start a new lecture. All right, so we'll start a new lecture next week. All right, so have a good weekend, and I'll see you on Monday.
Thank you.
Thank you, Professor.
Thank you.
Thank you.
Sir, I had a quick question.
Mhm.
So for the homework, for questions, for example, like this, do you want us to get it down to an exact number, or do you want us to leave it as at the formula?
So your formula is fine because numbers are meaningless, right? At this stage, as in like, it doesn't illuminate anything, right? What's important is you get down to like the answers that show, right? That you can get numerical values out of it if you want. Does that make sense?
So for example, like the fire station question, you wouldn't need us to go through the integration, or you think we should?
That's a different question. You have to, because
Okay.
the fire station, right? The answer is A in terms of lambda. You cannot, right? But here is a different question because here, right, it's just a numerical answer. These are not equivalent questions. Does it make sense? One is symbolically solve it down to the level. The other one is a numerical calculation. I don't care for numerical calculation, but yes, I do care that you solve it down symbolically down to the last step.
All right, sounds good.
Yep.
Thank you, Professor.
Yep, sure.